Guys, and a very warm welcome to this lecture. So in the previous tutorials we discussed about the architecture of Hadoop and how big data is emerging as new and very hot technologies in today's world. So in this lecture we'll be discussing some basic techniques on how MapReduce works, what is exactly MapReduce, and why do we choose MapReduce over other processing techniques. So MapReduce is one of the most successful realization of large-scale data parallel programming frameworks for large-scale data processing. It's the most suitable framework. So it's an open source implementation of Google's MapReduce. So Google gave out a paper regarding how they are processing data at their data centers, due to which later Apache got inspired out of it and used this into their implementation of Hadoop. So it incorporates two components, the first one being MapReduce and the second one being a distributed file system. So what exactly is MapReduce? So MapReduce is a programming model for big data processing. So when we want to process like 1,000 gigabytes of data, so it might take like a few days even to process it on an i7 core processor, but MapReduce does this in 207 seconds. So we can process 1 terabyte of data in 207 seconds. That's literally 3 minutes. So the power of MapReduce lies in its ability to scale to hundreds and thousands of machines, each with several processor cores. So how large an amount of work? So web scale data on the order of hundreds of gigabytes, petabytes, terabytes. It's likely that the input data set will not fit on a single computer. So mind you that we are using several core processors on several different CPUs, and we are first combining all of that data into one place, processing that, and then again data going back into their storage devices or their typical particular respected CPUs in which they are being stored. So where to store the big data? In a MapReduce cluster, data is distributed to all of the cluster nodes upon loading. So it's not just present at one place. So imagine like these, there are banking transactions that are recorded on a banking server. So we require how important is each transaction. So we would say that every transaction is really important for our banking server, our banking security system to function. We require all of that transaction. Even if one transaction is lost, we might lose a trace. So we need a fault tolerant distributed processing file system that can store data on multiple clusters, even if one CPU burns out or melts into flames. Let's just forget about stealing, like someone didn't stole our CPU, blasted and bursted into flames. What are we gonna do about the data? Like CPU, we can buy one more, but can we restore the data? The answer is, in case of Hadoop, is yes. So Hadoop splits large data files into chunks which are managed by different nodes in the cluster. So there are different nodes in our distributed processing file system, in our Hadoop distributed file system, on which we are storing our data. It's divided into small chunks stored on different nodes in the cluster. So this is our node 1, node 2 and node 3. So in these we are storing our data in racks, like rack 1, like the racks that you are having at the entrance of your houses where we keep our shoes. So racks, we are storing chunks of our data into nodes which are then again divided into racks. Rack 1, rack 2, rack 3. Say this is my one file of 1 terabyte. So first part of that file went into node 1 into my first rack. Then the second piece of chunk went to my second node on the second rack, and the third one went to my third node on the second rack again. So this is how my data is being stored on this distributed file system. So even though the file chunks or blocks are distributed across several machines, they are being managed under namespace. So commodity clusters. So MapReduce is designed to efficiently process big data using regular commodity computers. So I don't, supposedly me being a company, an industrial company, I cannot afford supercomputers or massive giant computing system. I can take afford some regular commodity computers. Sorry, I can afford to get some regular commodity computers. I can scale them to hundreds of thousands even, but I can only afford a regular commodity computer. I cannot afford a supercomputer, and when that runs out of space, buy another bigger, faster supercomputer. Instead, what I can do is I can buy regular commodity computers and add on to another CPU when the storage runs out. That is typically affordable for me. So theoretical 1000 CPU machine would cost you a very large amount of money, far more than 1000 single CPU, or like 250 quad core commodity machines. So premise: MapReduce ties the smaller and more reasonably priced machines together into a single cost-effective commodity cluster that can solve my big data problems. So that is why we choose MapReduce over any other framework in terms of big or large scale data processing. So like we were discussing, there's a name server, there's a namespace over here that is managing all of these clusters, and then there are slave nodes. So there's a master node and there is a slave node, and within these as well we are having nodes, different nodes, and within these nodes also we are having racks. So node 1 having 2 racks, node 3 having 2 racks, 3 racks, depending upon their own architecture, depending upon how we design their system. So this is also upon us, how do we want to design our system based upon the kind of data we are having, what kind of replication factor do we want to choose. So MapReduce assumes a tree style, a master-slave network topology. So master is controlling all the nodes while the slaves are controlling the data. So nodes are spread over different racks, as we were discussing earlier, contained in one or many data centers. So node 1 could be present over here in Indonesia, while the other node could be in California. So a salient point is that the bandwidth between the two nodes is depending upon their relative locations in the network topology. So supposedly node 7 here in rack 3 wants to communicate with node 1, so it can only happen through a master node. So their bandwidth might not be that great, but if node 1 wants to communicate to node 2, it will be really fast. For example, nodes on the same rack will have a higher bandwidth between them as opposed to the nodes that are off rack. So MapReduce divides the workload into multiple independent tasks and automatically schedules them on cluster node. So we are having this scheduled the task functionality over here, wherein we can schedule the tasks that, okay, when this processing gets done, I want to process these. So we are having this functionality of scheduling our tasks, which can help us divide the workload into multiple tasks, which can automatically be scheduled on cluster nodes. So a work performed by each task is in isolation from another. So one task, so supposedly I said the computer go get a pen, and after getting the pen refill the ink. So this task is done independent of another task. So when one task is scheduled, to prevent any intermingling of too many tasks, we prefer to keep them scheduled and organized. So any work that is performed is in isolation from another work. As we are scaling massive amounts of data, it's not like gigabytes or some like 1 or 2 terabytes. It can go up till petabytes, exabytes of data. So we want to keep everything organized. If anything gets mingled together, it's like folding of the hand-free or the headset wires through which we listen to music sometimes. So when that gets tangled, it takes really amount of effort to untangle those two pieces of wire. Imagine that happening with terabytes of data. So to keep things organized, we try to keep each task done in isolation from another one, and the amount of communication which can be performed by task is limited mainly from scalability and fault tolerance reasons. So as we discussed, if one CPU goes out and burns into flames of a banking server, the amount of transactions that were stored upon that PCs are gone. But in case if we used a Hadoop or any fault tolerant operating system where there are multiple copies of data, redundant data, which is being stored on multiple machines in different nodes, having this kind of scalability as well, which can help us do processing on commodity hardware, not requiring any supercomputers but giving us the power of supercomputer processing. So these are done for scalability and fault tolerance reasons specifically. The communication overhead requires to keep the data on the node synchronized at all times, which would prevent the model from performing reliably and efficiently at large scale. So supposedly we are having a data. Let us take a practical example. These are our storage mediums in our nodes. Say we are having a split of 3. We were discussing about MapReduce. So in the first part, what we did was, supposedly we are having a data. We are performing some MapReduce task. We first map our data. The first part of MapReduce is to map the data. Map and reduce. That means firstly we map the data and then we reduce the data. So we partition the data into different partitions. Then comes the shuffle stage, where we shuffle in our data. After shuffling in our data, we then partition them again. We merge those partitions and then we reduce, which is the reduce part of our MapReduce systems. So firstly, these are our data. We split our data or we map our data. Firstly we tokenize, then we map our data. Then after mapping our data, we do the shuffle stage. After doing the shuffle stage, we merge in our data. The merging part is our reduce phase. So this is all about MapReduce. Hope you guys enjoyed this lecture. In the next lecture, we'll be discussing about MapReduce with a closer look, and things will start to get a little more clear. Hope you guys enjoyed this lecture. See you in the next lecture. Thank you guys and happy learning.